All right, in 1662, Robert Boyle studied pressure-volume relationships. Now, he published his results, and it was about 140 years later that Gay Lussac and Charles Law studied volume and temperature relationships. Now, Lussac and Jacques Charles, they were balloonists, and so they would fill up their balloons and travel. While they were working with balloon technology, they needed to understand the relationship between temperature and volume. After that was in 1802 that they published their results. It wasn't until 1848 that Kelvin started to work on an absolute temperature scale. Now, in 1834, the ideal gas law was developed. Now, Boyle determined that pressure was equal to the inverse of volume. So pressure is about equal to 1 over volume. Gay Lussac and Jacques Charles discovered that there was a relationship between volume and temperature. Later on, these relationships, the three relationships, pressure, volume, and temperature, were put together in one equation that's now called the ideal gas law. And that's PV equals nRT. Pressure times volume equals nR times temperature. Now, we're primarily concerned with pressure, volume, and temperature right now. We'll talk about N and R later. In 1848, Lord Kelvin, William Thomson, started to work with volume and temperature, keeping pressure constant, decreasing temperature, and he noticed that the volume decreased as well. He worked with two gases, carbon dioxide and oxygen, and he was attempting to determine if there was a lower limit to temperature. Now, Sadi Carnot, in 1820, determined that there was a lower limit to temperature, and he came reasonably close. He determined the lower limit to temperature was about negative 263 Celsius. Now, Lord Kelvin determined with gas relationships, he used CO2, started out with half a gram of CO2, and let's put the zero scale over here. Zero is normally here, but we're going to put it here because we're going down into the negative region. We just want the y-axis over there for volume. The volume is going to be in milliliters. He used 0.5 grams of CO2 and then 0.5 grams of oxygen, 1 gram of CO2, and then 1 gram of oxygen. And let's just make these increments to negative 50. In increments of 50, so negative 50, negative 100, negative 150, negative 200, negative 250, negative 300, and I'm just going to say that's negative 350, and the increments won't be exactly even because this is just on the board. All right, now, I'm not going to make this exact, I'm just going to make this relatively decent. When he studied the temperature, as the temperature decreased, and he used Celsius, the volume decreased, and his volume 0.2, 0.4, 0.6, 0.8, and he used milliliters. The volume decreased as the temperature decreased, and he would plot the line, and that line went through the point negative 276. But he didn't know this at the time. Now, then he plotted the data for oxygen, half a gram of oxygen, and then he plotted 1 gram of CO2, and then 1 gram of oxygen. And I'm just randomly putting points up there. When he drew the best fit line through the points, through his data, he realized that regardless of the mass, all of the lines pointed to negative 273.15. Alright, so that was degrees Celsius. He used the Celsius scale. The significance behind this was that he was starting to determine that there is an absolute temperature, a lowest temperature. This, we later discovered, was the temperature at which particles cease to move. So negative 273.15 is the temperature at which particles cease to move. Volume decreases as temperature decreases. Okay? Now, he used the Celsius scale in order to determine this relationship. It was later, the Kelvin scale was later developed, and if you put this in equation form, Negative 273.15 equals Celsius. If Kelvin started out at 0 at negative 273, then the Celsius scale would have a temperature of negative 273. So if Kelvin is 0, Celsius is negative 273. So the equation just logically comes from the graph, K minus 273.15 equals Celsius. Alright, so Celsius equals this. If you add this to the other side, Kelvin is equal to, let me erase that, Celsius plus 273.15. Alright, now, since he used the Celsius scale, 1 degree on the Celsius scale is equal to 1 degree on the Kelvin scale. Alright, so you can, if you're measuring or using an equation or something like that, where it only involves a change in temperature, like if it goes from one temperature to another on the Celsius scale, and you need to later on convert the Kelvin scale, as long as you're only dealing with a change in temperature, you don't have to convert, because 1 degree on the Celsius scale equals 1 degree on the Kelvin scale. That'll make more sense later. All right, now let's look at the relationship between Celsius and Fahrenheit. We just came up with the two equations to convert between Celsius and Kelvin. Now let's look at Celsius and Fahrenheit. There are 180 intervals between the freezing point on the Fahrenheit scale and the boiling point on the Fahrenheit scale. So between 32 and 212, 212 minus 32, you get 180 intervals. That's 180 degrees. On the Celsius scale, the freezing point for water is 0 and the boiling point is 100. So there are 100 intervals on the Celsius scale. So that would be Fahrenheit over Celsius. You have a relationship here where 100 degrees or 100 intervals on the Fahrenheit scale is related to 100 intervals on the Celsius scale, so it's Fahrenheit over Celsius. Now, if you then simplify this, this becomes 90 over 50 divided by 2 is Fahrenheit over Celsius, and then divide top and bottom by 10, and you have 9 over 5. And this is starting to look familiar because you remember from 7th and 8th grade a 9/5 number stuck in the temperature equation. Now, if you then take this up here, 9/5 times Celsius is equal to Fahrenheit, you have an equation that is not quite yet correct. If Celsius is 0, Fahrenheit is 32. And with this equation, you don't get that. So what you need to do is add 32 to the left-hand side. All right, so 9/5 Celsius plus 32 is equal to Fahrenheit. And this is the equation that can convert between Celsius and Fahrenheit. Now, if you want to get Celsius by itself, we take this equation, we use algebra to manipulate it, and we get Celsius by itself. So 9/5 Celsius is equal to Fahrenheit minus 32. Multiply both sides by 5, divide both sides by 9, and you get Celsius is equal to 5 over 9, Fahrenheit minus 32. All right, we will call this equation 1. We'll call this equation 2. We will call this equation 3. We'll call that equation 4. All right, now, we have two other things that we need to look at. We can convert between Celsius and Kelvin. We can convert from Kelvin to Celsius and Celsius to Kelvin. We can convert from Celsius to Fahrenheit and Fahrenheit to Celsius. Now we need to convert between Fahrenheit and Kelvin, because right now we're using 3 temperature scales. If Celsius is equal to this, and Celsius is also equal to this, then this has to be equal to this. So Kelvin minus 273.15 is equal to 5/9 Fahrenheit minus 32. Okay? And if you want to get Kelvin by itself, you add 273 to the other side. Kelvin is equal to 5/9 Fahrenheit minus 32 plus 273.15. And now we have a relationship where if you have the temperature on the Fahrenheit scale, you can calculate the temperature on the Kelvin scale. Now, this would be equation 5. And finally, equation 6. You want to solve this for Fahrenheit. Multiply both sides by 9 over 5, add 32, and you get Fahrenheit is equal to 9/5 Kelvin minus 273.15, then plus 32 equals that, and that's equation 6. And these are your 6 temperature equations and how you can convert from one temperature to another.